Hello everybody, welcome to the Society of Aerospace and Robotic Engineers. I'm the President Martin Lopez Jr. and welcome to our new NASA Minds project. The new NASA Minds project we're working on is the Clinostat. The Clinostat is a device that simulates micromodel gravity conditions for specimens just like fungi, plants, and microorganisms. One of the microorganisms we're looking into is the Pseudomonas aeruginosa. This is a pathogen that's opportunistic, causing issues for astronauts in their labor up in space that we want to mitigate and do the betterment for their health. The impact that we could do with the features that we're adding in this new device that we're creating, or an innovative device that we're doing, is for automation, data collection, consistency with the data to have those model microgravity conditions, and as well making it cost effective. The cost effective can help both low-end and high-end institutes to understand model microgravity conditions, but as well as continue space research and aerospace research. This will help revolutionize space medicine and continue the Artemis mission when it comes to going into space, lunar, or Martian terrain. Here are some special words from our professor, Serrat Naguarama.
Our research laboratory focuses in the study of bacterial responses, including the impact on their capacity to infect, or virulence as we know it, to simulated microgravity conditions. Currently, together with students from the College of Engineering and Computer Science, we are working in the development of an enhanced microgravity simulator, or Clinostat. By using enhanced microgravity simulators, our objective is to best understand the space microbiome in space stations and near-Earth extraterrestrial environments, or NEES for short. This is with the purpose to best understand the space microbiome role in the development of disease in space crews and how to manage it.
Hello, my name is Jennifer Weina and I'm the Vice President and Research Lead for Sare. So our research team has 3 different subcategories. We focus on risk analysis, validation, and simulations. Our risk analysis team focuses on conducting trade studies to ensure any parts or material chosen is for good reason. Our validation team focuses on keeping extensive documentation so any data, testing, and general information used is reliable and accurate. And lastly, our simulations team runs simulations like finite element analysis and computational fluid dynamics to observe how our project will run in different settings and different environments. This includes different RPMs and different materials for our 3D printed parts.
Alrighty. So hi, my name's Sam and I'm the co-lead for the software, the telemetry team. And our goal as a team was to create a user-friendly interface for astrobiologists so that way they can use it for their research to promote the health of astronauts in space. And one goal we really had coming into this is we wanted to be super readable for people who were just looking at this for the first time. Because we know the HARV was designed originally without a user interface, so this was a brand new thing that we were taking on. So coming into it, we wanted it to be just super straightforward, very clean. And the way we were able to accomplish that was using tools such as React, which is a framework, and then Tori. And the languages we used alongside those were Rust for our backend and JavaScript for the front end. And using all these, we were able to accomplish that goal of creating a user interface for the HARV, and we're pretty proud of it, so thank you.
Hi, my name is Jonathan Ramirez. I'm Structures Lead and Secretary for Society of Aerospace and Robotic Engineers, and our goal for this project was to model microgravity. To achieve this on the structure side, we use CAD in SolidWorks to be able to model our design, and we took this model and then used 3D printing as well as molding to be able to achieve the parts that we needed to realize this vision. As for the power transmission, we decided to go with bevel gears so we had a reliable power transmission. And the polymers that we chose for the materials were PETG as well as acrylic. As for the PETG side, we chose these materials for their mechanical properties and the acrylic for the visibility of the specimen, as well as being able to mold it easily to make a non-porous vessel while utilizing gaskets to prevent leakage. With these tools, we were able to validate the structural integrity of the project and provide a physical model for the implementation of automation.
Hello, my name is Miguel Torres. I am the project manager and electrical lead for the organization. The goal for the electrical team is to be the bridge for telemetry, to communicate with any hardware, and be the embedded systems for the entire system. So the key components that we use is an ESP32S3, a DC motor, a linear actuator, and a gyroscope sensor. So The entire electrical system is based around the ESP32, which enables communication from the UI to any components in the electrical side. So any commands sent from the UI will control DC motor and linear actuator, allowing it to move forward or back, spin clockwise, counterclockwise, or control the speed from both, either one. And at the same time, the ESP32 and electrical side is able to send any data coming from the gyroscope sensor to the UI. So that way it has that two-way communication via ESP now. It's the protocol that the ESPs use to communicate to each other. And with this entire system is what makes the automation possible for the Clinostat. In short, with all components I just mentioned and a custom PCB designed by our team is what made a smart Clinostat and automation come to life.